Okay, folks, we are on the second chapter of this unit, Unit D, energy relationships in the biosphere. Solar energy is radiant energy transmitted as electromagnetic waves, and the symbol for that is lambda for EMR, electromagnetic radiation. The symbol is lambda. All the different types of EMRs exist in the electromagnetic spectrum. And let's take a look at these. Visible light is only a very small sliver of the electromagnetic wavelength. Okay, ultraviolet is on one side, higher weight, shorter frequency means higher, um, hi, shorter wavelength, sorry, means higher frequency. Here, the wavelengths get longer, longer wavelengths, lower frequency, less energy. Okay, and yeah, we just gone through that. Visible light is a very small range within the spectrum. Insolation is the amount of energy, solar energy, received by the Earth's surface. And the way you remember this is in, sol is Spanish for sun. Insolation depends on the latitude of the region. Also depends on the specific characteristics of the lithosphere, atmosphere, and hydrosphere. Not all regions of the Earth receive the same amount of solar energy. Angle of inclination refers to the degree to which the Earth's poles are tilted from the perpendicular of the plane of its orbit. And it's 23.5 degrees. So let's go through this here. So here is my Earth. And if it was, this is the orbit. It's spinning around its axis, okay? So that's the axis, and it's tilted at 23.5 degrees, okay, this way. And that's what that diagram is showing. Now this is important. Inclination, if I use the word inclination, I'm inclined to agree with somebody, means I tilt towards their argument. Okay, I'm inclined to agree. Now this is very important when we look at the seasons. It determines the seasons. Tilt on insolation, Earth once a year. On the first day of summer, angle inclination causes the North Pole to be tilted towards the sun, and vice versa in the winter, away from the sun. Longest day, December 21st. Northern Hemisphere receives more insolation during our summer months. Southern Hemisphere during our winter months. And we see that in this GIF here. It shows it nicely. Okay, so just read through that. Okay, solstice and the equinox. Angle inclination causes variation in the number of hours. Daylight, Earth can be divided into different latitudes, imaginary lines parallel to the equator. The equator, latitude 0, and the poles are at 90 north and 90 south. Remainder is divided equal parallel lines. So here we go. 90 degrees, 0 degrees. And these, Edmonton is right here. It's between the 50th and 60th parallel, or 49th, sorry, and 60th parallel. So the 60th parallel divides the provinces from the territories. A solstice is one of 2 points Earth's orbit at which the poles are the most tilted toward or away from the sun. The solstice occurs on June 21st and 22nd, has the most hours of daylight in northern latitudes and least hours in the southern. And the 21st and 22nd are our darkest, least hours. So that's a winter solstice. Summer solstice in the southern latitudes. At or near the equator, there's very little variation in the number of hours of daylight. Equinox is one of 2 points in Earth's orbit when the number of daylight hours is equal to the number of night hours. So here we go. We are going from the spring equinox, which would have been March, to June 22nd. October, we're going to have another equinox, winter solstice, so on in the northern latitudes. Okay, insolation and the angle of incidence. The shape of Earth also affects insolation of regions at different latitudes. So Earth is roughly spherical. Most incoming solar radiation is not perpendicular to the Earth, so it bounces. And the angle of incidence is the angle between a falling ray on a surface and the line perpendicular to that surface. Now look, I'll star this because don't get this confused with angle of inclination. That's different altogether. Okay, inclination is different. That's a tilt of the Earth's axis. So here we go. Here's my incoming solar radiation. Okay, it's going to bounce like that. But we have to draw this imaginary line here that this is perpendicular. Like I'll put a chair here, 90 degrees. And the angle at which it comes in is my angle of incidence, and the angle it bounces back from the normal, this big red line, is the angle of reflection. At the equator, the angle of incidence of the incoming solar radiation is 0. And I'll show that in a second. As one moves to the equator, the incidence angle increases. So look, this is 0. Incoming equals outcoming. It's like taking a basketball and bouncing against the wall. It is, there's my normal, the black line, we call the normal. And my incident ray is perpendicular. Here though, the normal is like this, yeah? There's my 90 degrees. Incident ray, reflected ray, angle I, angle R. Notice that in northern latitudes, when we have a big angle I, we get more area that the light lands on, but it's going to be less intense. Again, imagine getting hit in the face by a basketball or at the side of a face. Someone's going to get reflected off that energy. Earth's shape and angle of incidence play a large role in creating the Earth's climate. From the equator to the pole, there's a progressive decrease in insolation. Average annual air temperature is highest at the equator and decreases as one moves towards the poles. Number of hours of daylight varies progressively with the seasons, increasing higher and lower latitudes. More variation in average daily temperature throughout the year as one moves from closer to the poles. The poles. So more variation. So we're going to go from 30 degrees Celsius in Northwest or in Edmonton to minus 30 degrees Celsius. Well, that's a 60 degrees Celsius change in temperature. You're not going to get that in Singapore, which is right on the equator, which will pretty much stay at 30 degrees Celsius all year long. Okay, and we'll do this in the next lesson.